Hello my dear friends, welcome back again to Invisible Threads. Hope all of you are doing well in this struggling period. Please always wear masks while going out and stay safe. So today it is the continuation of our previous discussion. So we will discuss on the topic of electric potential due to an electric dipole. So let's begin. Electric potential due to an electric dipole. So as we all know that the dipole means two equal and opposite charges separated by a small distance of 2a. You can see from the figure this is plus q and minus q separated by a distance of 2a. And we have already calculated the electric field for a dipole in my previous video in the different position of the field point. So one is the point is on the dipole axis and this another one is when the point is on the equatorial plane. And we have seen that the electric field depends on the angle between the position vector r and the dipole moment small p vector. And this varies for the far distance as 1 by r cube, not like as 1 by r square like for the single point charge. So from this diagram you can see this is the AB is the dipole, where this in this point at the point B there is minus q charge, at the point A there is plus q charge, and we are trying to calculate the electric potential at the point P. And the dipole origin is at the center. So this is the r1 vector is equal to r minus a. This is the r2 vector, the distance between B and the point P is equal to also r minus a, and the dipole moment is acting towards B to A. So there will be the superposition principle will like the electric field will apply for the electric potential also. So we can write the potential VR at the point P, which is the position vector of the r, is equal to 1 by 4 pi epsilon naught times q by r1 minus q by r2. So from the figure you can see that r1 vector is equal to r minus a, and we can write that magnitude of r1 its whole square is equal to r1 dot r1. So it means r minus a dot r minus a. It means r1 square plus a square minus twice ar cosine theta, because you can see from the figure this is the r vector, this is the small a, so in between the angle is theta. Similarly for r2 square we can write it means r square plus a square plus twice ar cos theta, because this angle is pi minus theta. So again r1 square is equal to r square, if I common r square, so it means 1 minus twice ar cosine theta by r square plus a square by r square. So this term we can neglect because we choose that the point P is far away from the center of the dipole. It means r is very greater than a. So we can take up to first order of a by r. So r1 square is equal to r square times 1 minus twice a cosine theta divided by r. Similarly r2 square is equal to r square times 1 plus twice a cosine theta by r. This is our equation number 1. This is our equation number 2. So from equation number 1 we can write that 1 by r1 is equal to 1 by r times 1 minus twice a cosine theta by r whole to the power minus half. So this is from the binomial theorem. We can write that this is using binomial theorem. We can write that 1 by r1 is approximately equal to 1 by r times 1 plus a cosine theta divided by r. Similarly 1 by r2 is around 1 by r times 1 minus a cosine theta divided by r. Now the expression of V we have that V is equal to q by 4 pi epsilon naught times 1 by r1 minus 1 by r2. So if I subtract 1 by r1 minus 1 by r2, it becomes q by 4 pi epsilon naught times twice a cosine theta by r square. So it becomes 1 q by 4 pi epsilon naught times twice a cosine theta divided by r square. So now we can see that VR is equal to twice a q, we can common it, we can make it together, times cosine theta divided by 4 pi epsilon naught r square. So it means magnitude of dipole moment P, magnitude of dipole moment the small p vector is equal to twice a q, as we all know. It means the charge times the separation between them times cosine theta divided by 4 pi epsilon naught r square is equal to p vector dot r cap. It means the unit vector along the OP direction. So this is the OP. So this is the r vector. So the unit vector along the direction of the OP is r cap. So p vector dot r cap divided by 4 pi epsilon naught r square. So where r cap is the unit vector along the OP. So VR we can write the potential we can write is a function of the position vector r is equal to p vector dot r cap divided by 4 pi epsilon naught r square for r very greater than a. So this is the expression is valid for distances where the distance is large compared to the size of the dipole. So for the potential on the axis of the dipole, what we can get in that scenario, theta will be either 0 degree or 180 degree or pi. So V is equal to plus minus P divided by 4 pi epsilon naught r square. The positive sign comes out for theta is equal to 0 degree and the negative one is for theta is equal to pi. So we can see the main difference in electric potential due to dipole with compared to the point charge. So what is the difference, main difference with the potential of the point charge? The potential due to dipole depends on angle between r cap and the dipole moment and axially symmetric about the p dipole moment, because this is the, suppose this is the minus q charge here and this is the plus q charge, it consists a dipole, and suppose with the position vector is r vector making an angle theta with the dipole axis. So if I rotate the r vector about p, this is the dipole moment direction, in this direction this is the dipole moment direction. So you can see it make a cone, and over the circumference of the base of the cone in this line, this circular line, you can see there is the same potential because there is only theta dependence, no r dependence. For fixed r there is only theta dependence. So we can, and the another one is that electric dipole potential varies as 1 over r square, not like 1 by r as the point charge. So we have understand that for point charge V varies as 1 by r, whereas for dipole the potential varies as 1 by r square, and the electric field for the point charge it varies as 1 by r square, whereas for the dipole E varies as 1 by r cube. Now we can go and we want to see the potential distribution for a system of charges. Suppose in a space there are few charges like q1, q2, q3 and q4, and we try to calculate the potential at any arbitrary point p here, and the distance from the q1, q2, q3, q4 from the p is r1, r2, r3, r4 respectively, you can see from the figure. So the potential v1 at point p, so you can see the potential v1 due to the charge q1 at point p, what it will be, v1 is equal to, for a single point charge, what it will be, v1 is equal to 1 by 4 pi epsilon naught times q1 by r1. Similarly v2 is equal to 1 by 4 pi epsilon naught times q2 by r2. V3 is equal to 1 by 4 pi epsilon naught times q3 by r3. So from the superposition principle, the potential V at the point P, we are trying to calculate the potential at the point P. Due to all the such charges distribution, what it will be, V is equal to all the potential, individual potential will add up for the individual charges. So V is equal to V1 plus V2 up to Vn, and it brings 1 by 4 pi epsilon naught sum over n Qn divided by Rn. So we have continuous distribution of charge, and you can see that with the volume charge density, suppose we have some continuous distribution of charge and we have some volume charge density of rho, which is function of r. Then in each element, suppose delta V, we consider some small element delta V, and so the charge contained in the volume is rho delta V. Then for each element we need to find the potential, individual potential, and then we can integrate to get the potential for the total charge configuration. So our next topic of discussion will be on the equipotential surfaces. So let's see what is this. So this is the equipotential surface. We will now discuss on the equipotential surface. So from the name we can understand that it is the surface over which there is a constant potential. Equipotential means there is a constant potential. So for a single charge we can write point charge q at a distance r. What it will be, the potential will be, as we all know, Vr is equal to q divided by 4 pi epsilon naught r. So we can see for a fixed value of r, the potential is constant, and for a point charge the equipotential surface are concentric spherical surfaces. You can see from the figure, this is the plus q charge and the electric field lines are getting outward. So I have drawn some concentric spheres, both have the center at the plus q, but the value of the potential is different for different spherical surfaces. So we have understand that for the point charge the equipotential surfaces are spherical. Similarly, we can write this is for the uniform electric field. You can see this is uniform electric field in the direction of the electric field. So the equipotential surfaces are always perpendicular to the direction of the electric field, and this is the flat surfaces. Similarly, this is the equipotential surfaces for a dipole. you can see where the charges, this is for the -1, this is for the +1. So in between them, the distance between the two concentric spheres get closer, and in the other side it is wider. So for any charge configuration, equipotential surface is normal to the direction of electric field at that point. Why? As we already get to know that the work done to move any charge in between any two points in the difference. So suppose I move from one place to another place, 1 point charge. So what is the work done that I have done? So the work done is a change in the potential energy between the 2 points. It means I need to product the potential times its charge. But for the equipotential surface, there is constant potential with no variation. So there will be no change in potential energy. So if we try to move any charge under the equipotential surface, we will see that the work done is 0. So how to prove that under the equipotential surface the work done is 0? Work done W is equal to charge times the change in the potential VA minus VB in between A and B. For the equipotential surface, as we all know that there is constant potential, so VA is equal to VB, so the work done is 0. So now for our question, how can I prove that the electric field is normal to the equipotential surface? Suppose we can see that the electric field is not normal. So this is the equipotential surface, and I choose that the electric field is not normal, making an angle theta with the base of the equipotential surface. So it has the component around the potential surface is E cos theta, and perpendicular direction is E sin theta. So suppose I move some work done in moving some charge Q by a length of elementary length dl over the equipotential surface, what it will be? W is equal to F dot dr. So the force is equal to Q times E. So the charge is Q, and the electric field along the equipotential surface direction is E cosine theta. QE cosine theta is the force, and the distance is dl, the small displacement. So the work done, this becomes 0, because from the equipotential surface, as we all know that the work done to move any charge over the equipotential surface is 0. So from there we can get that the value of cosine theta is equal to 0. It means theta is equal to pi by 2. So this angle what I have assumed is not other than theta is equal to pi by 2. Therefore the electric field must always be normal to the equipotential surface. It means theta is equal to pi by 2. So my friends, I am pausing my discussion here. If you have any kind of difficulties, don't hesitate to let me know, and please do like, share and subscribe our channel as much as possible with your family and friends. Stay tuned and keep supporting. Thank you.